Okay, this session is mostly going to be hands-on. I'm going to talk for a little bit, but not that much. Okay, in this session, we're going to talk about code coverage and continuous integration testing. So first of all, code coverage is something that helps us determine what other tests are needed. You have some test suite, and you want to determine whether you're actually testing all of your code. So code coverage tools, they are capable of exposing parts of the code that aren't being tested, and the ones that we're going to go over today are gcov and lcov. Gcov is a standard utility with the GNU compiler collection suite, and what it does is it counts the number of times each statement is executed by your test suite. Lcov is a graphical front end for gcov. It's available there, but gcov is usable on its own. I just kind of like the pretty pictures. How you use gcov and lcov, first step is you compile and link your code with the coverage flag, and it's a pretty good idea to disable optimization, just because when optimization's on, then sometimes it'll give you misleading statements about the number of times that things were executed. Then you run your test suite. You collect coverage data using gcov or lcov, and then optionally you can generate HTML output using gen.html, which is a tool that comes with lcov. So we're going to switch over to our hands-on gcov tutorial. It is at this website here, so if you could go to the website listed there, then we can start the tutorial. So if we still have our sticky notes, if you could go to that website and then put up your green sticky note when you're done on your computer, so that I know that everybody has made it to this website. So Morpheus is this fake little project that I set up for this tutorial. It's a code that contains a vector class and a matrix class. And I wrote some tests, because of course I had to write some tests for my fake little code. And what we're going to do is we're going to determine whether my tests are any good or not. So to do this tutorial, you should log on to Vesta. Or if you don't want to use Vesta, it doesn't technically have to be Vesta. It's just any machine that has the GCC compiler suite. After you get onto Vesta, you clone the Morpheus repository, and we've already learned about how to clone things from Git. We follow this command, git clone. You go into the Morpheus directory, you make your tests, and then you run your tests. After you run the tests, we're going to analyze the results with gcov to determine what my code coverage looks like. And I know I'm going through this really fast. I'm not expecting you to actually do it as fast as I'm saying it. But I'm going to leave you guys alone for the next maybe 20 minutes or so to do this with the code, to download it, to build it, to run the tests, and to see what the code coverage looks like. And then we're going to talk about the code coverage and about the test suite itself. So if everybody could now take down their Post-it notes, when you're done analyzing the code and admiring it, please put up the sticky note. If you are having any trouble, please put up the red sticky note. And then when everybody is ready to talk about the code, we'll talk about the code. The instructions are, go check this code out of my GitHub repository. Apparently some people thought I said that I was going to check my email and you guys were free to do whatever you want. That is not actually what I said. I said, please check out the repository so that you can do some experiments with it. After you check out the repository, build the code, run the tests, and then use gcov to analyze the results of those tests. Look at the results, see which tests which lines of code were actually executed by the tests, which ones were not, which pieces of the code would you trust, which pieces of the code would you not trust. Go look at the code, see the places that I didn't test, and determine whether my code is buggy or not. That is our task for the next 20 minutes or so. And if for whatever reason you can't get gcov running, at the very bottom of this web page, if you click the link at the very, very bottom of that web page, amclinv.github.io, clicking that link will pull up the code coverage report for this code. So even if you aren't able to generate the code coverage report yourself, you can go read it and follow along. And when you are done with all of these things, please put up your green Post-it note. As you start analyzing the results of gcov, what you'll see is each line will be preceded by either a number or a set of pound signs. If a line of code is preceded by a set of pound signs, like here, that means this line of code was never, ever, 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 ever executed by any of the tests in the repository. This line of code was executed 125 times. This line of code was executed 150 times, et cetera. But we are looking for the lines of code that never, ever, ever got executed. So we're going to proceed. And even if you weren't able to complete the exercise, that's OK. You have the information for later. You can always go back and look at it later. How much confidence do you guys have that my code's correct? Because I gave you some code. I gave you a test suite, right? It's tested. Oh, you don't like my code. Why don't you like my code? Like what key parts doesn't it test?
Matrix multiply.
The matrix multiply. What's wrong with my matrix multiply? I have a test for it, don't I? Actually, I don't remember. Did I have a test for it? OK, I never bothered to test that one at all. OK, so I have key routines that are not tested. What else, apart from the fact that I have key routines that aren't tested? What other problems do we see with my code?
I just got your head.
It's OK. You don't have to come up with one. Oh, how are the matrices bad for my tests?
These upper triangular type tests.
Why is that bad? Is my upper triangular function actually correct? So somebody brought up that the matrices that I'm using in my tests aren't great matrices. And this has nothing to do with the code coverage itself. Like that function is reporting that it's reasonably well covered, right? Some of the matrices I'm using are not great for my tests. Like I'm testing my is symmetric, is upper triangular. I was testing one of those functions with the identity matrix, and that's a really specific matrix that wouldn't trigger a lot of problems. So what should I be using instead of the identity matrix?
A random one.
Basically anything else, right? Maybe not a random one, because then we wouldn't know whether the test should pass or fail. But maybe some predetermined random one. So we got some percentage of my code that's covered, and it was not 100%. If I remember correctly, it was like 40-some% of my code that's covered. Even if my code had 100% code coverage, would you trust it to have no bugs? I'm hearing some no's. Why wouldn't you trust it to have no bugs? Does 100% code coverage mean no bugs?
On your test case, does it? And actually there are bugs. So.
There are absolutely bugs in that code. Please don't actually use this code to do real science. It has bugs in it. It purposefully has bugs in it, or at least I will pretend that every bug was on purpose. I'm sure some of them were by accident, but most of them were on purpose. No, so what we're learning from this is code coverage, it can't give you an assertion that your code is fine. It can't tell you what you're doing right. It can only tell you things that you were doing badly. If you run the code coverage tool and it says that you never bothered to call the matrix multiply function, well, that's obviously bad. I should have a test for my matrix multiply function. But it can't tell me that I did good things. So it is kind of a depressing tool in that respect. What other issues do we see with my test suite? Nothing else is wrong with my test suite. We're all happy with it. What's that?
The dot product is not tested.
The dot product's not tested. And if I remember correctly, I used integers. I used positive integers for all of my tests. What kind of errors could I fail to pick up because I'm using positive integers in all of my tests?
You're missing an absolute value.
I'm missing all kinds of absolute values. I think I was missing an absolute value for some of the norm functions. And it didn't matter. My test passed because the input data was really easy. So realistically, I should be using different types of input for my tests. You have to put a little more thought into your test suite than just am I calling every single function? You have to make sure that you are testing the edge cases, the cases that will be actually hard. If my test failed, would it be easy to track down the source of the problem? So I gave you guys a script to run my entire test suite. And it was just some, I think it was a Perl script, maybe it was a Perl script, maybe it was Shell. But I gave you a script to run my entire test suite. And I don't think it tells you if one of the tests fails, which one actually failed. So maybe if I did that, it would make it easier to track down a problem if something actually started failing. Okay, so maybe you don't use C++ and this gcov stuff just doesn't really apply to you. Fortunately for you, gcov also works for C and Fortran. And even though gcov doesn't work for other languages, there are similar tools for other languages. Like if you're using Java, you can use jcov. You can use coverage.py for Python, devel cover for Perl, profile for MATLAB, and other tools for other languages. Now we're going to turn our attention to continuous integration testing. Continuous integration, the goal of that is a master branch that always works. So in continuous integration, the code changes trigger automated builds and tests on targeted platforms. The builds and tests should finish in a reasonable amount of time, providing useful feedback when it's most needed. This is why I said earlier that maybe continuous integration testing is not right for Trilinos. Trilinos is an awfully big package. It takes a while to build it. It takes a while to run the tests. But for other libraries, it might be immensely helpful. But it does require some work. It requires a reasonably automated build system and an automated test system with significant test coverage. That's where gcov comes into play. You want to make sure that you are testing everything that you mean to be testing. And you need a set of systems on which the tests will be run and a controller. Continuous integration has existed for some time, but adoption's been slow because setting up and maintaining the continuous integration systems is difficult, labor-intensive, and sometimes it requires a dedicated staff member. Also, you have to be doing a lot of things right to even consider continuous integration. You need to have a test suite, first of all, in order to do it. Cloud-based continuous integration is available as a service on GitHub. The automated builds and tests can be triggered via pull requests or commits. Builds and tests can be run on the cloud systems, so that's a great use of the cloud. And the test results will be reported on the pull request page, as I will show you, with links to the detailed logs. It's already being used successfully by scientific computing projects with noticeable benefits to productivity. And it's not perfect, but it's far better than not doing continuous integration. Travis CI is a good choice for high-performance computing because it integrates really easily with GitHub. I don't think it integrates as easily with GitLab, but GitLab has its own internal thing. Travis CI is free for open source projects, which immediately makes it really attractive. It supports environments with C, C++, and Fortran compilers, including GNU, Clang, and maybe Intel. I'm not so sure about Intel. It has Linux and Mac platforms available, and it's relatively simple, it features a relatively simple, reasonably flexible configuration file. The documentation used to be sparse, but they now have working examples. But I think the best way to learn Travis CI is to actually see Travis CI. So if we go back to my wonderful Morpheus project, which is at github.com/amclinv/Morpheus. If we go here and we scroll down, not that far, if we scroll down to my commits, we'll see that I set up continuous integration for this repository. And you see that all of my commits have a special symbol next to them. They're either going to have a check mark or a red X. What do we think these check marks and red X's mean? Pass or fail. Yep. My building and testing either passed or failed. So if we look at specific commits, we see that on February 28th, 2017, earlier this year, Travis continuous integration testing was run on this commit, and the Travis CI build failed. If we click on that, we can get more information. It pulls up Travis CI. I set this up to run with both Clang and G++ on Linux and Macs. That's why we see 4 different builds here. And we see that it failed on every single one of those builds. So I'm going to pick my favorite one. I'll pick the Linux G++ build. And if I click on that, it'll tell us exactly what happened in the build. So the commit that broke everything was the one that removed an unnecessary semicolon from the matrix class. And if we scroll down, we see that there was a build error. And Travis CI helpfully recorded that build error for us. Error expected semicolon after class definition. Oops, apparently in that commit, when I removed the unnecessary semicolon, it was actually kind of necessary. I make this mistake all the time. I remove semicolons from the end of classes. They have to be there. So Travis CI gave us a lot of useful information. Oops. And if we go back to the repository, then we see that my very next commit was the one that replaced the semicolon removed in the previous commit, and that one succeeded. So Travis CI is pretty cool because you can look at your repository and immediately know whether you've broken things or not according to your test suite. But how hard is it actually? The Travis CI information is recorded in a file called travis.yaml. And we're going to open it up. But before I open it up, I want to know how scary we think this file is going to be. Do we think my travis.yaml file is going to be really, really scary? I like the enthusiasm. I thought the Travis CI was going to be absolutely terrifying. So let's look at it. The scary stuff is just off screen. Oh, no, oops. Apparently there is no scary stuff. This is a 12-line YAML file. All that's in here, it says that my code is C++. That's what the top line says. It says I'm interested in running my code on 2 operating systems, Linux and OS X. I'm interested in using 2 compilers, G++ and Clang. And then I give it a script to build my code and run the tests. To build my code, you just type make, because I have make files. To run the tests, I had my helpful test running Perl script. That is my entire Travis CI file. So does it now seem more reasonable that you could set up Travis CI for your own projects and it wouldn't be terrible? Even if you used, I know this is a really simple example where we're just using make files and I have like 3 source files. We have a little Perl script that runs our tests. But if you were using, let's say, CMake and CTest, it still wouldn't look much more complicated than that. You would just have CMake, make, CTest, and that would be it. So this is a little baby repository that's not real. Let's look at an actual repository of real code. This one is not on GitHub. This is GitLab. But it's a real project that I work on called Tucker MPI. And what it does is it does data compression for simulation data generated by DOE simulation codes. Right now, scientists are generating terabytes of data at a time from a single simulation. We can't store it all. So this code takes it, compresses it using the power of math, and then stores that compressed data. But it's not terribly important what the code does. It's just important that this is real code. This isn't some toy project. And we're going to look at the continuous integration file for this project to see if it's any scarier than the other one. Noting that it's going to be a little bit different because that one was using Travis CI, this is using GitHub CI, and they're really similar but not quite identical. So is this file going to be terrifying while it loads? You've been spooked out too much already? You already saw the cat jump out. You know this time it's not going to be an alien. It's still going to be the cat. I'll make it a little bigger. OK, now that I've made it bigger, we can see it's still the cat. It's not the alien. The first line of this says that we are going to import a Docker image to set up our environment, and the Docker image I'm using is GCC 6.3. Before the script is executed, I'm going to install the dependencies of my software. That's all this says. My code depends on CMake, it depends on OpenMPI, it depends on BLAS and LAPACK and some other things. So all this line does is install all of my dependencies. If we scroll down, the build stage is going to create a build directory. It's going to call CMake, and then it's going to call make. That'll build all of my code, all of my tests. And then I said that the build directory is an artifact. Please keep it around. You don't necessarily have to do that. I just chose to keep it around. In the test stage, we go into the build directory. We call ctest, and this says that if ctest fails, if one of my tests fails, it's going to output why it failed. And then at the very bottom, this has absolutely nothing to do with testing. This has to do with automatic documentation generation. I've tied that into the continuous integration as well. So every time I touch my code now, my code is going to get built, the tests are going to run, and then it's going to update the Doxygen documentation every single time I touch the repository. And if we look at my commit history for this repository, we'll see that it looks similar to our little baby repository that we were playing with before. So all of my commits still have the same check or X next to them. So whenever I broke something in this repository, I think we have to scroll down pretty far to see me breaking something. There we go. If I break something in this repository, it's accompanied by a red X. I realize it's broken immediately. I fix it. That commit happened like right after the previous one. So Travis CI is really helpful, or GitLab CI is really helpful for this project. I've left plenty of time available at the end so that you can try out any of this stuff with your own projects, and I'll be here to answer questions. Let me see if I had any more slides first. I did not have any more slides. OK, so if you guys want to talk about code coverage and continuous integration as it applies to your own projects, then I'd be happy to answer questions for you.
Even if we could do something.
Like how much time you spent on that project, maintaining that infrastructure?
How much time I've spent maintaining the continuous integration?
Building, setting up the automated document generation.
OK. So for my real project, not Morpheus, the actual real project, Tucker MPI, it took probably a couple hours to set up the continuous integration testing, and that was just because that project has so many dependencies. But after that, I've spent maybe an hour maintaining that, because at one point somebody updated their Docker image, and that was the Docker image I was using. So when they updated the Docker image, it broke everything. I spent a little bit of time downgrading to their previous Docker image, and that's the only time I've touched that file in the past 6 months. So it's really not an impediment to my work.
Can you have multiple stages for the integration testing, or is that all part of the script that you execute, and then you need to check back or log at which point the testing broke? So the unit testing, integration testing, if you want to have the full stack.
Oh, OK. So I'm using ctest, meaning all of my tests get run by ctest. And I'll pull it back up. It doesn't care how you run your tests. You can run your tests however you choose. You just have to tell it the command to run those tests. And here I just did a C test. That's going to run all of them. It's going to run my unit test. It's going to run my system level tests. It'll run all of them.
Like the output file will always be like one Travis or one CI output. It's not that you will set up different tests for different levels.
Can you repeat that question?
So, you will always have like one test suite and the result is success or fail. It's not that you can set up multiple levels of testing independently and then see where, like at a higher level, you have failed.
Oh, I'm sure you could. Yeah, I just chose not to do that. In my mind, it doesn't matter if it's a unit test that fails or a system level test that fails. If it fails, it will notify me that it failed. I'll get an email saying that it failed. It'll appear on the dashboard. It will say exactly which test it was that failed. So that's fine for my workflow.
How can I have these tests running on different architectures?
So again, this is different based on whether you're using Travis CI. I think Travis CI kind of makes it easier. But on GitLab, if you're using GitLab CI, then you can just use different images, like Docker images, for whatever architecture that you're planning to support.
Are you using a shared runner here
A share runner?
for doing the GitLab CI? I guess you can use shared runners. It's like cloud-based with their own resources, or you can set up a private runner, right? And I don't have any experience with private runners. And I was just curious because when I started setting up something like this, I noticed that I had to make my own image with all the dependencies compiled to run out of time before I could even start running my tests. So
Yeah. Yeah, realistically, I am planning at some point in the future to make my own image so that I can import it. I just haven't had a lot of luck getting Docker to run on any of my machines. That's its own story. Yes?
So what is best practice with regard to external libraries that are not available as a package and also need to be embedded and compiled in the image?
Embedded and compiled in the image?
Yeah, I mean, if there is no, if oneself doesn't want to set up, I mean, I guess you can set up your own Docker image, but
Yeah.
if you want to pull in external libraries, then you need to compile as well. What is the best practice there? Should I prepare a Docker image? Should I put all the compile commands into the before script part, or how should I tackle that?
I guess it depends on how long it takes to build those libraries, because there is a set amount of time that you are allowed to spend building and testing your code.
I actually just built an MPI, build it from source, and then on Travis you cache the installation. So the first time you do a build, maybe you don't add any tests, but then you cache your MPI installation, then it loads in like 10 seconds, and you save a lot of time.
Thank you. Hi.
Hi, so I'll ask the question I asked you earlier. So say you want to run remotely on different types of architectures. Say you want to run like a KNL node or a PT node or something, some other kind of remote cluster or something. So what kind of, I asked you if there was any remote feature. You weren't sure. So is there someone in here who has more experience with running the test remotely on some other type of cluster with specific hardware requirements?
So I'll repeat the question for the people on the other side of the room that might not have heard it. You are asking about running these tests not on the types of machines that I'm running on, but running them on large clusters. Is there a way to tie that in with the continuous integration testing? Does anybody have an answer for that?
So I think somebody mentioned it down there, but I think you can, with the shared runners, I think we do tests that, like Nurse on Core using GitLab that will run on that.
So that facilitates basically queuing up some jobs, submitting it, and coming back.
I think so.
For most of the leadership class machine installation, it's not the technology, but the policies that are the problem.
To my local HPC center, so we use, there at Michigan State, we have a Red Hat cluster that servers and Torque PDS, so I'm trying to figure out how to integrate integration of my particular projects and stuff with that regard. So,
I think you can just use this type of functionality so that you can load the environment on your own machine.
Yeah, you might have to install a private runner on that local machine and then configure your repository to let you run your CI there. I don't think it's trivial to do.
Yeah, and as we've seen, the continuous integration itself is not going to present a challenge on its own. The little 12-line YAML file need more of a challenge than that.